In this video, we are taking a look at a couple of sections combined from the author Larson 6.2 and 6.3, differential equations, separation of variables. I'm just taking out what I think is the important parts and to include and maybe not including everything, so I kind of lumped it all together. The main ideas here are going to be separation of variables, and we're going to look at some exponential growth and decay and something from that called Newton's law of cooling. And that's all we're going to focus on in this particular video. Now, differential equations, obviously the entire courses are taught in this, or you may have not think you have to take differential equations, but many courses disguise it in other names like engineering math and so forth. All right, so with that being said, let's take a look here. Now, the idea of what a differential equation is, it's an equation where one or more variables consist of either a y prime first derivative, y double prime second derivative. I guess they could be more involved than that if possible. But this is, you're trying to find the solution for y. Now, these first two examples in this top row are not problems we're solving in this particular class. Separation of variables is only one technique for differential equations. There are many more. So we won't be solving either one of these top two here, but I'll just kind of like to take a look at the one on the right. So the one on the right says you're trying to find y such that y double prime plus 5 times y prime plus 6 times y itself would equal e to the negative x sine of x. And actually, anytime you're doing an antiderivative, you are solving a very elementary differential equation. So in other words, if you have y prime equals x3, you take that antiderivative, turns it into y, and that gives you 1/4 x to the 4th plus c. So obviously, you can't build an entire differential equation course just on that. So you've actually been solving them and not even realize that's what it was. Now, this technique of separation variables means we have to do a little bit of algebra, and we have to separate where we want x and dx on one side of the equation, and we want y and dy on the other. Then we integrate both sides. Now, some problems it'll tell us we want to isolate y explicitly. Others we will not. We'll just leave it in implicit form, which is a combination of x's and y's without y being by itself. For example, problems that would lead to like y squared, we would not want to solve in explicit form because you have the whole plus and minus issue. Then we'll integrate both sides. So like I took that same problem from above and wrote it as this dy dx equals x cubed. Move the x cubed, dx over with the x cubed. Integrated both sides. So the antiderivative of dy would be y. Antiderivative of x cubed dx would be 1/4 x to the 4th plus c. Now, the very common question is, wouldn't there be a plus c on both sides? Now, there isn't really a need for c on both sides. It's basically c is a c, so to speak. So the general rule to do this is you put it on the side of where the x is, or whatever the other independent variable is. Obviously, differential equations could be, like dy dt or something like that. So the idea is to put it with the non-y side, because you don't need plus c's all over the place. So let's take a look at this one. Dy dx equals x squared plus 2 divided by 3y squared. Now, this one's pretty easy to separate algebraically. You just kind of cross multiply, and you've got it in one step. So 3y squared dy, there we go. And this way you have x squared plus 2. And then you integrate both sides, so the antiderivative of 3y squared dy will be y cubed. And the antiderivative of x squared plus 2 would be 1/3 x cubed plus 2x, and then your plus c. And like I said, we'll solve for y only when we're asked. So sometimes if you're looking at other answers, I don't know why they do this, but I've seen answers in books. You look up the answer, and you might see something like this. Sometimes they'll set it equal to the c, and sometimes they'll multiply. This one, they just got rid of the fraction. I mean, they're all equivalent. They're all correct. For some reason, they must not have wanted that fraction there. But keep in mind, when you multiply something like 3 times c, it doesn't change it to 3c. It's still just c. So that doesn't affect anything. All right, so that's just different ways to write it. So let's take a look at this one. We're going to say we're going to solve for y on this one. So we're looking for some function y where dy dx equals 4 minus y. One thing I'm going to mention is just, obviously when you take an integral in theory, sometimes integrals are too complicated to have time to do this, but obviously you should be able to differentiate the answer, to see if you get what you started with. But keep in mind with these x's and y's, you would have to do this. Since it's not explicitly solved for here, you would have to use a technique from Cal 1 called implicit differentiation to be able to solve this. And if you used implicit differentiation, you would see this derivative does match the original problem. But that's not generally a mandatory step that you have to do. Maybe your particular instructor might would ask it. I would not. But so dy dx equals 4 minus y. So first thing I did, and I could have, I moved the dx up and over there. I didn't show that step, but bring the dx up. But now I'm showing that you would have to divide both sides by 4 minus y. So now we do that. So the 4 minus y is on the right cancel. And we have dy over 4 minus y equals dx. Okay, that means the variables are separated. The y's are on one side, the x's are on the other. Now you integrate this. Obviously the right side's easy. It's just the antiderivative dx equals x. And then if you let u equal 4 minus y, du would be negative dy, so negative du equals dy. So this integral becomes the negative of du over u, which is automatically natural log. If that's du over u to the first, the antiderivative, so it's negative natural log of the absolute value of 4 minus y. And then you have x plus c on the right. Now I want to solve for y here, so I'm going to need to apply e to it, but first I've got to get rid of this negative, so I'll multiply both sides by negative 1. And it's important we make this negative x, but actually it doesn't really matter if you make that a negative c or a positive c. I went ahead and made it a negative c, but it would make no difference in what's about to happen here in the next couple steps here. So it makes no difference. It's still a c. Now with that negative gone, I can apply e to both sides, because e gets rid of natural log because they're inverse functions. So e to the natural log of the absolute value of 4 minus y would just leave the absolute value of 4 minus y. Then on the right side, we have e to the negative x minus c. And property of exponents, show you a little trick here, e to the negative x times e to the negative c. So this technique will be pretty handy not only for this class, but when you go on to something differential equations related. So anytime you have e, you'll see this happen. Is that, well, e, since e is just a number, e is also a constant, so e to the minus c is strictly just considered a c. It's just a constant c. So you can actually take e to the minus c, that would, it could be e to the plus c, that's why it didn't matter. E to any kind of c can come out here in front and just be a constant c. So that will happen every time that we have this e with something here. So now so actually if you remove the absolute value, that puts a plus and minus on this right side. And then if you solve this for y, just move the y over, move this other. You basically have two solutions, but really it's kind of one solution. So really, because the c can be positive or negative, so you could leave it as plus or minus, or really either one of those is correct. And I'll show you on the next page. So, but I could have just written this as one solution, y equals 4 plus and minus c e to the negative x. So I actually decided to check both these answers. And I'm going to show you that they're both correct, which means either or both would have been fine. So the original problem was dy dx equals 4 minus y. So that means the derivative of our answer here needs to equal 4 minus our answer. So I did this, so the derivative of this side, because the derivative of e to the negative x is negative e to the negative x, so it makes it positive c here. And then I have 4 minus our answer, 4 minus c e to the negative x. The 4's cancel, makes that negative positive, so that checks. These left equals right side. That works. Same thing for the one with the plus. It's going to work also. You'll have negative here. You'll have negative here. I put this in maple. Maple put the plus there, which is fine, but that goes along with my argument, meaning plus or minus wouldn't matter, because what if C was just a negative number, then that would just make it minus. So you'd have been good with plus or minus or both. Anyway, anything's fine there. So, okay. Let's take a look at this next example. We're going to say solve for y here. Let's take a look at separation. This is a little trickier than the last one. So I just rewrote y prime as dy dx right here. And okay, so let me bring the xy over to the other side, subtract it, bring it to the other side. And now I have dy dx equals 100x minus xy. So, how am I going to get this separated? Well, when I looked at this point, I looked at this and go, well, how about if I factor an x out of there? Because obviously, if you've got multiplication, you can divide, on both sides to get rid of something that's multiplied. Right now, division wouldn't do me any good here because that's the subtraction. So an x comes out of here, and that leaves 100 minus x times 100 minus y dx. So I can keep the x and the dx together. Now I can divide both sides by 100 minus y. So now I have dy over 100 minus y equals x dx. So this problem is going to be very similar to the last one, because we just said we had 4 minus y. So I didn't even show the integral, because it's going to be exactly like the last problem. So now it's going to be just negative natural log of the absolute value of 100 minus y. The antiderivative of x is 1/2 x squared plus c multiplied by negative 1. Once again, I left the c as negative. You can leave it positive. We don't care. We e both sides right here. So that turns it into 100 minus y, absolute value, e to the negative 1/2 x squared minus c. So I skipped a couple steps here because it's using exactly the same process as the last problem. You would split these up. Actually, once you get comfortable, you don't need to split them up. Once you see this with e, only when it's e with e, you know that's going to be a c that hops down right in front, right here. So with e, that will be automatic every time. Other functions, not so much. Because it is possible you could have something to where the something plus c could be in the parentheses if you had to apply some other function. Let's say if you had, for example, I'll just say x plus c or whatever, and let's say you're having to, maybe on the right side, you're having to, let's say we're having to use either like tan or tan inverse or something like that. Well, anyway, if you have to apply tan to both sides to get rid of tan inverse, for example, you would have like this. It would not turn, the c wouldn't turn into multiple. You would literally have an answer that says tan of x plus c, like that. It's only the e that does that. Okie doke. And let's see what we have here. So we have, and then it becomes y. It's not, see, I just left it as plus and minus this time. Once again, Maple solved it as plus. I put the c right there at the end. I don't know. That's fine, but like I said, plus or minus, either way would be correct. Okay, let's look at something called finding a particular solution. Let's see what that's all about. All right. Now this says, this means we are allowed to have information that would let us solve for C. Meaning we're given an initial condition here where, like, y of 1 equals 2. That means we'll be able to solve for the value C at the end. It's sort of like back in Cal 1, where we had those first doing antiderivatives, and you see like it would have like f of 1 equals 5 or something. That means you could solve for the C. So that's what's going on right here. So let's see what we have here. All right. 2xy prime minus ln of x squared equals 0. And we have then the y of 1 equals 2. So I'll rewrite the y prime as dy dx. So we have 2x dy dx equals negative. I always like to use log properties whenever possible because it makes things a little simpler. So log properties say I'm allowed to bring that 2 down. So that's what that's going on there. It's not a derivative or anything. It's just log property. Equals 0. Well, I just went ahead and divided out the 2. Yeah, I moved it over, and either way, divide the 2 out. So I did this next thing in one step. You know, if you're not comfortable doing this in one step, that's fine. But I looked at this and I said, okay, so I have x dy dx and equals ln of x. I looked at it and said, hey, if I just multiply it by dx over x on both sides, so dx over x will kill the left side, and then it will leave x's only on the right. So I go, that then leaves dy. So that worked out perfectly. But if you would have brought the dx up first, then divided by x, you do whatever makes you comfortable. So if you need that extra step, that's fine. So dy dx equals ln of x dx. Okay, of course, the antiderivative of dy will be y. That's simple enough. Now, the next integral is not too bad. It's just straight substitution. If you let u equal ln of x, du would be 1 over x dx, and it fits perfectly. So on the right side, your integral just becomes u du. And so that's then 1/2 u squared. So the general solution means with the plus c. So see, this one we don't have a multiplied plus c like we did those other two problems. So it's y equals 1/2 ln of x squared. Now we don't bring the 2 down here. See, when the log function is raised to a power, you don't bring the exponent down. It's only when the argument of the function is raised to the power. And so plus c. So now that would be fine if we didn't have this initial condition. That would be our general solution, but now we can solve for c, because when x is 1, y should equal 2. So I put 1 in for x, 2 for y. ln of 1 is 0, so it zeroes out all this, and I get c equals 2. So there would be the actual particular solution. Y equals 1/2 of natural log of x squared plus 2. All right, so I played around in Maple a little bit here. And there it is. 1/2 equals natural log. Okay, this is kind of the way they do it. I don't really like it, but that's Maple's notation. That's not natural log of x squared. It means the natural log is squared. They do that with trig functions too. I kind of wish they would wrap another set of parentheses around it, but that's okay. The point is that is correct and matches my answer. So, all right, let's take a look at this example. We have so y times dy dx equals negative x cos x squared. So I did the dy dx, and so we have y of 0 equals negative 2. That's our initial condition. We will find the particular solution from there. I bring the x cos x squared over to the right side, and then to separate this will be easy enough, because all we have to do now is just multiply both sides by dx, and it will be perfectly separated. We'll have the y's will be on the left side, the x's will be on the right side, and we're good there. So it wasn't too much algebra there. So, all right, this integral is not too complicated, because if you let u be x squared, du gives you 2x dx. 1/2 du equals x dx, so everything fits beautifully here. And so let's come on, and then of course the antiderivative of y would just be 1/2 y squared. So you see they both had 1/2s here, so I went ahead and just canceled them now. I could have dealt with it later if I wanted to, but I just went ahead and took them out. You know, it's the same thing as multiplying both sides by 2. So that gives me antiderivative of cosine of u would be sine. So just to save a step, I didn't write sine of u. I went ahead and replaced what u was in one step there, which that's fine. So I have y squared equals sine of x squared. We're not solving this one for y. The last problem, it didn't tell us to solve for y, but it just worked out naturally where y was on the left side because we integrated dy. Here, with the square, the y squared, there's no way I'd be asking to solve for y. So we have sine of x squared plus c, and then I put in 0 for x and negative 2 for y. So I'll put in 0 there. So that gives me sine of 0 squared. I have negative 2 on the left, so negative 2 squared. And that's going to give me a 0, so c would equal 4. And then so I just take my particular solution right there. General solution right here, and replace C with 4 to get our final answer, which is the particular solution. Okay. All right, let's see. This is telling us then to solve for y. And so what am I going to do here? First step, I'd bring the dx up and over. That's usually a good idea. And then, okay, well, I got to get rid of what's in the parentheses there. That would leave the x's on the right. So divide both sides by 4 plus 9 squared. And so we have dy over 4 plus 9y squared equals x squared dx. Now the right side is going to be easy enough because it's just 1/3 x cubed. The left side is not too bad. See, it falls into tan inverse, arctan. You know, I'm pretty flexible. I wrote arctan there. Obviously, it doesn't matter, but that works either way. So u equals 3y because it'll be 9y squared. The a will be 2 because it's the square root of 4. Du is 3 dy, so that brings a 1/3 over. Du equals dy. So I have a 1/3 here on the outside of this for the du. I have a 1/2 because the formula is 1 over a. And I have arctan of u over a, 3y over 2. I just canceled out the 3's immediately. And then I also, well, I could have, I guess, just multiplied both sides by 6 in one step. But, okay, that's fine. I could have multiplied both sides by 6. But it was okay. Anyway, arctan of 3y over 2 equals 2x cubed plus c. Now, I mentioned this earlier when I wrote that kind of with the thick pointer here and mouse pointer that, if we had to apply tan, I forgot that was actually going to be coming up, but that's good, though, because now we can see it in a real problem. So to get rid of arctan, I apply tan to both sides. But unlike E, when I apply tan to that right side, the C doesn't automatically become a multiple of it, and you don't split out the C. So you literally just leave it as tan of 2x cubed plus C. Just like that. So the plus C stays in there with it. So that tan kills arctan, leaves 3y over 2. So you multiply both sides by 2/3. And it's kind of funny how Maple did this. Maple has a 6 multiplied by the C, but that's okay because basically a C is a C is a C. So, 6C doesn't hurt anything there. Which if I'd multiplied both sides by 6, it would have been a 6C there, but I promise you, when you think about it, if you take the derivative of this and the derivative of this, the derivative of 6c or the derivative of c itself would still be 0 because it's just a c. So don't let the Maple thing make you think that I actually messed this up. So I guess there is a little interpretation on that. So, but C is good enough. Okay, let's take a look at this one. All right, this one just took a couple of quick steps here. Basically, if you move this over and you divide both sides by what's in the parentheses, that will get the x's and the y's separated. Here's what I actually did. Technically, I simultaneously divided both sides by what's in the red here, and then it separated it for me. But once again, you don't have to do it that quickly if you're not that comfortable. And all right, this one's kind of interesting. Notice that both intervals are the same. I mean, they're different variables, but they're exactly the same. So however, when you integrate one side, the other side will be exactly the same, just with the other variable. So I just like the left side should be let u equal 1 minus y squared. Du is negative 2y dy. So it makes it negative 1/2 du equals y dy. So, and then the antiderivative of u to the negative 1/2, when you bring this up right here, I didn't show that, but obviously when this comes up right here, it's negative 1/2. Makes it 2u to the 1/2, so the 2's cancel. So you basically have negative u to the 1/2. And on both sides now. So you just have to, so it's so 1 minus x squared on the right will be the exact same thing. So I got rid of the minuses. It's not wrong to leave the minuses there, but I went ahead and got rid of them. We're not trying to solve for y or anything here. I just thought it looked better without the negatives. So the exact same integral. And then what was our condition here? Y of 0 equals 1. So if I put 0 in for x and 1 for y, I can solve for that c right there. And I'll have 0 equals 1 plus c. And then c equals negative 1. So there would be my final answer. I don't know what I was doing over here. I guess I was just taking the implicit derivative of the general form or whatever. Don't worry about that. I don't know why I didn't do the desolve there or whatever for this one, but that's okay. It doesn't matter. We did it. We did it correctly. We did fine there. So, all right, growth and decay models. Let's take a look at this. So suppose that the rate of change of a variable y, which rate of change is derivative, is proportional to the value of y itself, and if y is a function of time t, we're saying that dy dt equals k times whatever y is. In other words, k is that proportional amount right here. So it's also called the constant of proportionality. Now I'm going to do a quick differential equation solution here, and you're going to see that we're just going to use this answer. You don't have to solve this one ever again. You can just work with it in this form. So this is just showing you where it comes from. So I'm solving this for y. So I divided both sides by y. K is just a constant, so I left it over there with t. So I have dy over y equals k dt. And I so it'll be ln of y equals kt plus c. So we e both sides. So now here's the deal, because we're doing the e thing again. That will bring the c out in front of the e attached to it. So y equals ce to the kt. And there you go. So that's the exponential growth model, growth and or decay. It's the same model. The only difference is that if it's a growth model, k will be positive. If it's a decay model, k would be negative. So it's not two separate equations. So k is your proportionality constant, and c will be the initial value of y. So let's say at time 0 we had 1,000 bacteria or something like that. That would be the c. Okay. So this is telling us the rate of change of p is proportional to p. So that means we use that model. When t equals 0, p equals 5,000. And then when t equals 1, p equals 4750. What's the value of p when t equals 5? I remember one time somebody asked me in class, well, if it's decreasing by 250, can't we just keep decreasing it 250 per each t? And I'm going, well, that would be fine if it was a linear model, but it's not a linear model, so it doesn't decrease like a slope. So there went that idea. That would have made it too easy, but yeah, if it had been a straight line, that would have been right. But E is not a line, it's a curve. So t equals 0 tells me p equals 5,000. So right off the bat, then that's going to tell me that I know that c will be 5,000 because it's whatever p. Yeah, and you can actually plug it in there and see, because if t is 0, that takes e to 0 will be 1. So 5,000 equals c. So yeah, so that's why that would be correct. But here's where that, the t equals 1, p equals 4750. That's how we're going to get our value k. Now you can already see by looking at these numbers, this is going to be a decay model because it's decreasing. The value of p is decreasing, so it's going to be negative. So I took that. I know that. So here's the general model. We don't know what k is. P equals 5,000 e to the kt. When t is 1, I know p is 4750. So I divided both sides by 5,000, got 0.95 equals e to the k. We natural log both sides to get rid of the e. And so we have k, a natural log of 0.95. It doesn't really matter that much. I guess on a written exam, I would tell you the number of decimal places to use. If it was a multiple choice exam, it probably wouldn't make that much of a difference, but use about 4 decimal places, I think, would be good enough, just to make sure it's okay. Negative 0.0513 equals k. You see it right there. So this is our official model. P, and I could have put P of t there if I wanted to write function notation. but P equals 5,000 e to the negative 0.0513 t. So now you can figure out what P will be at any time t. So I'll put 5 in there. And of course, this is, it didn't mention in this problem. Now, obviously, once again, I wouldn't try to trick you on a test, but some problems, like the next one, if this was supposed to be bacteria or supposed to be something that was measured in a whole number, that's why I just rounded it the nearest whole number. I just pretended like it was going to be something that it had to be a whole number answer, but it would see whatever the instructions in the problem say, that's good enough. But like I said, bacteria for sure would be something that's a whole number, even if it didn't tell you that. So we're expecting about 3869 to be the value at time 5, t equals 5. So as expected, it's decreasing. All right, so we got a little 4-part problem here. Bacteria of a culture is increasing. There are 125 bacteria in the culture after 2 hours and 350 bacteria after 4. So we got to find the initial population. So notice they're not telling us time 0. But that's very important that they gave us 2 other points in time, because we have to have both of those to be able to solve for the time 0. So we'll come back and look at all the questions here in a minute, but let's just find C first. So I just use B for bacteria. Yeah, I mean, you can use Y every time. It's not mandatory. I used P because the last one said it was P. This one I just use B, but I mean, you can use Y. I just use B for bacteria. So B of 2 at time 2, we got 125. B of 4 is 350. So what I did is set up 2 equations here. 125 equals CE to the 2K, because T is 2. 350 equals CE to the 4K. So now we have 2 equations, 2 unknowns. C and K are unknowns. So you can just substitute one into the other. So I took the first one, solved for C by dividing both sides by e to the 2K, and then I'm going to plug that in right here into this other equation. So that's what I did. So I took the 125 divided by e to the 2K, plugged it in for C. So you combine those exponents. 4K minus 2K is 2K. 350 divided by 125. So divide both sides by 125 to get rid of this, because to apply ln, I need the coefficient of e to be gone. So I divided by 125. That came out to be 2.8. So once the coefficient of e is gone, I can now apply natural log to both sides, and that gets rid of the e. So I have 2k on the right, ln of 2.8. So k will equal 1/2 ln of 2.8. So there it is, all in one step there. I just decided to wait, and not get the ln of 2.8 first. I just did it all at once. So I used 4 decimals and said roughly 0.5148. Now C needed to be a whole number, so I rounded here. So I already have C up here, so I can say that C equals 125 over e to the 2 times that 0.5148. So I'll put the squiggly for approximate here. So you see right there, 44.64. So I think normal rounding is fine. You can round up if it's 0.5 or above, and down if it's less. So I chose 45. So this is, so part B was asking write the exponential growth model. So now we have K, we have C, so there's your model. B of T equals 45 e to the 0.5148 T. So that means now we can find the bacteria at any point in time we want. Determine the number of bacteria after 8 hours. Okay, so once you have all that work done, this is really easy. Plug in the 8 for T. Put in the calculator. Notice how I wrapped parentheses around all of that. Very, very important. Because if you cut off the parentheses too early, that will not give you the right answer. Because it would not include the 8 with the E. So very important. And so we're saying about roughly 2766 bacteria after 8 hours. How many hours? So now we're going to be solving for time. I'm saying, okay, we're allowing 2 decimals because, obviously time, unlike bacteria, could be measured in terms of increments that aren't whole numbers. So that's okay. So we're looking for time that takes the bacteria to grow to 25,000. So we replace the B with 25,000 and we solve for the T. So once again, I get rid of the 45 because we know we're going to need ln to bring that t down. Divide both sides by 45, and e equals 0.5148. So I went ahead and didn't divide here. I left it as a fraction. So I put ln in front of it, ln on both sides. And then that means it would be 0.5148t. So you divide both sides then by 0.5148. So I just did this all in one step. So I left ln of 25,000 divided by 45, all divided by 0.5148. All in one step. Roughly 12.28 hours. As per instruction, we said 2 decimal places. Newton's law of cooling. I'm not going to go into the actually deriving of this formula like I did for the initial growth and decay thing, but we'll just start with it as is. So let's take a look at this. And Newton's law of cooling essentially applies. The idea is you take something, an object, and a heated object or whatever, and you introduce it into an environment at a lower temperature. Then you want to calculate how long would it take to cool down to a specific temperature. Like here, an example. Okay, let's suppose you cook a turkey and take a turkey out of an oven, maybe somewhere between 160 and 180 degrees, and you want to know how long it's going to take that turkey to get to maybe 100 degrees, and that's where you're going to start cutting it. Let it cool down a little bit. We can solve for that. But of course, that's based on the environment that the turkey is sitting in. All right. So now y0 in this formula is the temperature of the surrounding environment. So take the turkey out of the oven and put it in a 70-degree room. Y0 would be 70. Now you got to be careful. So obviously put this, have this written down so you'll know a little bit different what C means this time. C is a little bit different than it was for the regular growth model. C is defined as the initial temperature of the object minus whatever y0, the environment temperature, is. So if that turkey was 180 degrees and the surrounding environment, the room temperature, was 70 degrees, C would be 110. It would be 180 minus 70. All right. When an object is removed from a furnace and placed in an environment with a constant temperature of 80 degrees, its core temperature is 1500 degrees. That's pretty hot. I wouldn't want to play with that, whatever that is. 1 hour after it's removed, the core temperature is 1120 degrees. Find the core temperature 5 hours after the object is removed from the furnace. Okay. Y0. Back up here. 80 degrees. Initial temperature. So here's the key. C is not 1500. It's 1500 minus 80. That temperature we brought it into. So the C will be 1420. Okay, so that's very important. And then now we're okay. We know after 1 hour it'll be 1120. So that means when T is 1, Y will be 1120. Okay. So now that when T is 1, I know 1120 will be the left side. So we're trying to solve for K, that proportionality constant. Then that will allow us to calculate what the time will be, the temperature at any time. All right, so we have, so I subtracted 80 on both sides. Got 1040 divided by 1420. So it's 1040 divided by 1420 equals e to the k. So we ln both sides. So I just left this. I didn't divide this. And ln kills e. So k will equal ln of 1040 divided by 1420. So I just used 4 decimal places and said negative 0.3114. And you are expecting this to be negative because it is a cooling process here. So this is our model here. Y of t equals 80 plus 1420 e to the negative 0.3114t. So find the temperature after t out, 5 hours, no problem. Put in 5 for t. And I don't know, well, I can't give you a good explanation of why I didn't use all 4 decimal places up there for that exponent. I have no good answer for that. So, but I'm at least acknowledging, so you see that. I don't even know why, but anyway, that's all right. Probably should use 3114, but I'm not going to change it now. It's not going to make that much of a difference. I mean, I could put it in a calculator and show you, but or you can check if you want to yourself, but it won't matter much. I mean, obviously, it would allow a little bit of margin of error. If it was a handwritten test on the multiple choice exam, there's no way I would have answers that were like 381.3, 381.4, 381.5. So they wouldn't be all that close together. So I put the 5 in there. So we're going to say after 5 hours, whatever that thing is cooled down to a nice chilly 381.4 degrees. I still wouldn't want to play with it. So that's the basic gist of Newton's law of cooling. Let's take a look at another example here. That will wrap up our section. A container of hot liquid is placed in a freezer, kept at a constant temperature of 20 degrees. The initial temperature of the liquid is 160. After 5 minutes, the liquid temperature is 60 degrees. How much longer will it take for the temperature to decrease to 30 degrees? Now the wording on this one's a little bit tricky, so you got to read this carefully. So it's asking for how much longer beyond the 5 minutes. So what we're going to end up solving for is we're going to say how long does it take to get to 30 degrees. So let's just say hypothetically that's not going to be isn't going to be the right answer what I'm about to say, but let's say it took a total of 15 minutes to get to 30 degrees. So really the correct answer for the question would be, if it says after 5 minutes, how much longer will it take? Well, it would be 15 minus 5 means it would take 10 additional minutes. So 15 total, but 10 beyond that original 5. All right, so okay, so we have 20's initial temperature. C will be 160 minus that initial temperature, so it's 140. And after 5 minutes, we know it's 60, so T is 5, Y is 60. So I subtracted 20 to get 40 over here, then divided by 140. And equals ln of e to the 5k. And ln both sides, so you have 5k here, ln of 40 over 140. So k equals ln of 40 divided by 140, all divided by 5. So using 4 decimal places, negative 0.2506. Now we want to know, so I'm solving now for the total time it gets to be 30 degrees. Well, so we want to know 30 degrees, so that's y here. And so there we know, and once again, I cut this off to 2 decimal places. I don't know why I did that, but I did. So it's that same negative 2506 right here. So 30 minus 20 is 10, and I got a little cute here too. So let me explain what this is. Maybe I shouldn't. I didn't do it here, but I decided, oh well, I decided that I just went, well, 10 divided by 140 is the same thing as 1 over 14. You can get rid of the zeros there. I didn't have to do that. Okay. Sort of regret it now, but that's at least now that I've explained it. Hopefully if you watch this, it won't be so confusing now. So 30 minus 20 was 10 divided by 140. Yeah, so 10 over 140 is the same thing as 1 over 14. Then once again, I don't know why I didn't use all the decimal places here, but we're gonna get close enough here for government work here that it'll be all right. We're not totally butchering the problem or anything. Maybe I looked at it and saw 2506 and just said, the heck with it, just use 25. I don't know. So you take the ln of 1 over 14 or 10 over 140 and divide it by negative 0.25, so it's roughly 10.56 minutes. Of course, I need to specify how many decimal places. That would help. Well, anyway, so it's a total of 10.56 minutes, but the actual answer to the question is 5.56 additional minutes from the original 5. So so it's 5.56 beyond the initial 5 to get to 10.56. So a little tricky on the wording, but the math wasn't too bad. So Well, all right. Well, that concludes this video on differential equations, separable differential equations, and applications.